Hello everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम लोग केमिस्ट्री की क्लास करने वाले हैं, जो कि केमिस्ट्री की क्लास की अगर हम बात करते हैं तो ये 147th क्लास है। ऑलरेडी हमने 146 क्लासेस कर लिया है, जिसमें ऑलरेडी हमने हाउ टू कैलकुलेट द इक्विलिब्रियम कंसंट्रेशन जो लास्ट हमने स्टेप्स डिस्कस किए थे। फर्स्ट ऑफ ऑल, अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुंचे। एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो सो दैट ज़्यादा से ज़्यादा लोग के पास वीडियो पहुंचे और ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सकें। In today's topic, we will discuss the relationship between the equilibrium constant, reaction quotient that is Q, and the Gibbs energy that is G here. In regard of that, before starting with this, we have to know some of what related to the equilibrium constant that is K, reaction quotient that is Q, and the Gibbs energy that is G. With regard of that, the value of the Kc for a reaction does not depend on the rate of the reaction, and however, as we had studied in the many previous units as well, it is directly related to the thermodynamics of the reaction, and in particular so to the change of in the Gibbs energy that is of delta G, what we had learned about it. If delta G is negative, then what it says that if delta G is negative, then the reaction is spontaneous and proceed in the forward direction. So it will be the spontaneous, and that will be moved toward the forward reaction here if it is negative. When we are talking about the delta G is positive, if it is positive, what it then the reaction is considered the non-spontaneous, and that will be a non-spontaneous, and as well as instead as an average revenge reaction, it will be the reverse reaction as when it is positive, and that is the reverse reaction here. Here with reverse reaction, and instead as reverse reaction would have a negative of delta G, as you know very well, and that the product of the forward reaction shall be converted to the reaction as well. Now we'll talk about the another one, that is when delta G is 0 here. In terms of that, so when delta G is your 0, then the reaction has achieved equilibrium at the point, and there is no longer any free energy left to drive the reaction here. So now with this, a mathematical expression for this thermodynamic view of equilibrium can be described by the following equation, that is your delta G is equals to what delta G is equals to delta G plus R, that is your ln, and RT, that is ln Q here, where this delta G, if I'm talking about with this G, that stands for the Gibbs energy. Okay, and at an equilibrium, when delta G is equals to 0, then that Q is equals to Kc here, and with regard of that, the equation will become that is delta G, that is of delta G subscript, that is a Gibbs energy, plus RT L log K, and equals to 0. And when we are putting on this value, then further delta G subscript is equals to minus RT L log K, and we will go ahead with L log K here, that is equals to minus of delta G, that is of Gibbs energy, change in Gibbs energy upon RT, and further that taking anti-log of the both side, we will be finding out here we'll take it out that taking anti-log, then we'll find it out K equals to E power minus delta G, that is of Gibbs energy, by RT. This will be finding out right. Hence, using these equations, that the reaction spontaneity can be interrupted in the terms of the value of delta G subscript. And with regard of that, if the delta G subscript, if I'm talking about the delta G subscript that is equal less than 0, then the answer would be minus delta G subscript by RT, that is positive, and that the E ki power will be that at minus delta G by RT. This is a subscript, and then we have RT that is greater than 1 here, and with regard of that, that making K equal is greater than 1, which implies a spontaneous reaction, or the reactions which proceeds in the forward direction to such an extent that the products are present predominantly. When we are talking about the delta G subscript that is greater than 0, here that minus delta G subscript by RT is negative, and where we will be finding out that value minus delta G subscript by RT, that is less than 1 here, and that K is less than 1, which implies a spontaneous reaction or a reaction which proceed in the forward direction to continue such a small degree. Only a very minute minute quantity of minute quantity of the product that is formed here. With regard of that, now we'll discuss the one of the questions here, and that what we have to discuss here. The question we have here is that the value of delta G minus, that is of Gibbs energy, for that is your phosphorylations of glucose is glycolysis is 13.8 kg per mole inverse, and that is per mole, and that is the find the value of the Kc at 298 Kelvin. Here the delta G is equals to, you have they had given you 13.8 kilojoule mole here, and that is converted into the joule kilojoule से joule inverse में करेंगे तो 13.8 into 10 to the power 3, ये किलो का ये 10 to the power 3 joule mole inverse यहाँ पे आ जाएगा. And also we can say that delta G minus is equals to minus RT log Kc, जो कि अभी हमने ऊपर निकाला है, and log K जो हम Kc निकालते हैं that is equals to minus 13.8 into 10 to the power 3 joule mole, that is 8.314 joule mole inverse, and Kelvin inverse, and that is multiplied by 298 because the temperature is 298 here. Now we'll find it out the log Kc, that is equals to minus 5.569, and that Kc is equals to e की पावर माइनस 5.569, जो कि यहाँ पे निकल के आया है. e की पावर माइनस Kc था, तो that Kc has been find it out, and we find it out the Kc is equals to 3.81, as you can see 3.81 into 10 to the power minus 3. This will be the finding of the value of Kc here in terms of when the temperature is 298 Kelvin, and where we are finding out for the delta G has been given here. Now we'll move ahead with another one, and that is another question here that what we have to discuss. As you can see, the question is that the hydrolysis of sucrose gives that is the sucrose plus H2O, it gives glucose plus fructose, or we can say that glucose plus fructose gives sucrose plus water. Equilibrium constant, that is Kc, for the reaction that is 2 into 10 to the power 13 at 300 in Kelvin. So calculate delta G at 300 in Kelvin here. Now we'll find it out, and we'll do a solution here for this, and that is for that we have to know that delta G of subscript is equals to minus RT log K CE, and that is delta G subscript that they have given minus RT. If I'm talking about here, so here we have been given is your that is R is minus 8.314 joule mole inverse Kelvin inverse multiply 300 in Kelvin multiply log 2 into 10 to the power 13 here. When we further solve it out, then delta G is equals to, that is minus 7.64 into 10 to the power 4 joule mole inverse. This will be the answer when we are finding at the temperature we have been given as 300 in Kelvin here. Now we'll move on further, and then we will discuss about another topic, and that is the factors affecting the equilibria, that as you can see here in this, that one of the principal goals of the chemical synthesis to maximize the conversion of the reaction as we go further in it. And we can say that to produce while a minimum the expenditures of energy, this implies the maximum yield of the product at a mild temperature and the pressure condition as well. If it if does not happen, then the experiment conditions need to be adjusted, like for example in the Haber's process for the synthesis of the ammonia from N2 and H2, and that the choice of the experiment condition is of real economic importance, and annual world productions of ammonia is about 100 million tons, primarily for the use of the fertilizer as An equilibrium constant like Kc that is independent of the initial concentration, but if the system at equilibrium is subjected to a change in the concentrations of one or more of the reacting substances, then the system is no longer at equilibrium and net reaction takes place in some directions until the system reaction is the equilibrium once again. And similarly, a change in temperature or pressure of the system may also alter the equilibrium, and in order to decide what course of an reactions adopts and make a qualitative prediction about the effect of the changes in the conditions on equilibrium, that we use the Lee-Chatelier's principle, and it states that here and that a change in any of the factors that determine the equilibrium condition of a system will cause the system to change here, and to change in such a manner so as to reduce the counteract the effect of the changes here, which this is applicable to all the physical and the chemical equilibrium. And now we'll discuss more of the factor that is influenced by the equilibrium, and that we have the effects of the concentration change, and we go ahead here. Here with the effects of concentration change, we'll go on with these equations and the graphs. First, we have to know about the effects of the concentration change, that in general, when the equilibrium is distributed by the addition or the removal of the reactants or the product, that is your Chatelier's principles predict that the concentration stress of an added reactant and product is relieved by the net reaction in the direction that consumes the added substance, and the concentration stress of the removed reactant or the product is relatively relieved by the net reaction in the direction that replenishes the removed substance. Or in the other word, we can say that when the concentration of any of the reactant or the subproduct in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to make sure the effect of the concentration changes. Let us take the reaction which is mentioned here, that is H2, that is in the form of the gas, give plus H2 that is in the form of the gases. It will give 2Hi here, that is in the form of the gases as well. If H2 is added to the reaction mixture of the equilibrium, then the equilibrium of that reaction is distributed, and in order to restore it, the reaction proceeds in a direction wherein H2 is consumed, and that is more of H2 and I2 react to form HI, and finally the equilibrium shifts in the right and a forward direction. And this is in accordance with the Lee-Chatelier's principle, which implies that in the case of the addition of reactant and a product, a new equilibrium will be set up in which the concentration of the reactant and the product should be less than that what it was after the addition, but more than what it was in the original mixture here. With regard of that, we will discuss here a graph that is represented, and that is the effect of the addition of H2N on a change of the concentration of the reaction of the product in the reaction, that is H2 gases in the form of the I2, and that gives the 2Hi. Yeah, that will give that 2Hi in the form of the gases here. As you can see here, this is a graph where it represents the Hi, and this is the H2, and that is I2. H2 is gone to the constant, this was the equilibrium. In a equilibrium state, it goes towards an T1 temperature at a high, and then after that it will goes to the cross to the T2 temperature, and equilibrium re-established, and this is of not at equilibrium at T2 here. And for the H2, that is H2 is added in here only. And with respect to the time, we are concluding this. And for the I2, it goes to it is in the equilibrium, and then after that it goes slowed down, and then it was re-established here, and that equilibrium is re-established. And under this T1 to T2, this there is not equilibrium is established, and there is no equilibrium has been seen here. With regard of that Hi, this is also in the equilibrium. After the T1 temperature, it will not at equilibrium state, and it will goes and again equilibrium re-establish after the T2 temperature here. This is what we have to say, and that same point can be explained in the terms of the reactions of the question Q, that is Q is equals to Hi whole square, that is of 2Hi, and upon H2 and I2 here. With regard of that, if I'm talking about that, the addition of the hydrogen at the equilibrium results in the value of the Qc being less than Kc, and thus in order to attain the equilibrium against a reaction moves in the forward direction. Similarly, we can say that the removal of the product also boosts the forward reaction and increases the concentration of the product, and this has a great commercial application in the case of the reaction as well. And where the product is a gas of or the volatile substance in the case of the manufacture of ammonia, or ammonia is liquefied and removed from the reaction mixture so that the reaction keeps moving in a forward direction. Similarly, in the large scale production of CaO, that is used as important building material from the CaCO3, and the constant removal of CO2 from the cleanse drives the reaction to completion. It should be recommended that the continuous removal of the product maintains Q, and at that value less than Kc, and the reaction continues to move to the forward direction as well. In that react we can go ahead with another one, that is the effect of concentration as an experiment. An effect of concentration and experiment, here you can see, and as we'll discussed so on, and that is the effect of the concentration and experiment here. Before starting with this can be demolished, demonstrated by the following reaction that is represented, that is Fe3 plus in aqueous state plus SCN minus, that is in aqueous state, and gives FeCN2 plus an aqueous state. This for the Fe aqueous, if I'm talking about, this is yellow in color, and this is SCN, that is in the colorless. And for the FeSCN minus, that is in aqueous state, that is we have as your deep red. Okay, with regard of that, here reddish brown जिसे कह सकते हैं हम, and the Kc we find it out that FeSCN, that is 2 plus, that is in aqueous state, upon Fe3 plus aqueous and SCN minus aqueous here. This is how you find it out the Kc here. A reddish color appears on adding the 2 drops of 0.002 m potassium thiocyanide solution of 1 ml of 0.2 iron nitrate of the solution due to the formation of FeCN SCN2 plus that it forms here, and the intensity of the red color becomes the constant on attaining the equilibrium, and this equilibrium can be shifted in either forward or the reverse reaction, and that is depending on the choice of adding a reactant or a product. That equilibrium can be shifted in the opposite directions by adding the reagent, and that remove the Fe3 or CN minus ions. For example, like oxalic acid की अगर हम बात करते हैं, we have to talk about the oxalic acid, that we can say that H2C2 and O4 here, that reacts with Fe3 plus ions to form the stable complex that it forms will be Fe C2O4 thrice and 3 minus. This that what they had formed, and here, and that thus the decreasing on the concentration of the free Fe3 plus aqueous. In accordance with the Lee-Chartas principle, the concentration stress to be removed Fe3 plus is relieved by the dissociation of FeCN2 plus to the replenish the Fe3 plus ions, and because of the concentration of FeCN2 plus decreases, the intensity of the red color decreases. Here, with regard of that, the addition of the aqueous HgCl2 also decreases red color because Hg plus 2 react with the HCN minus ions to form of stable complex ion, that is what they form is your HgSCN4 2, that what they form, and the removal of free of Cn minus aqueous shift the equilibrium in the equation, and from the right to the left replenish Cn ions. Addition to the potassium thiocyanate on the other hand increases the color intensity of the solution as shifted in the equilibrium to the right here. Here we'll talk about moreover about the effects of the pressure change here. Starting with the effects of the pressure change, that we have to know about effects of the pressure change here. So where the pressure changes obtained by the changing the volume, that can affect the yield of the product in case of the gaseous reaction, where the total number of the moles of the gaseous reactant and the total number of the moles of the gaseous product are different. In applying the Lee-Chartas principle to the heterogeneous equilibrium, the effect of the pressure changes on solids and the liquid and can be ignored because of the volume, and the concentrations of a solution that is liquid is nearly independent of pressure. And we are considering the equation, that is carbon monoxide in the form of the gaseous state plus 3H2 in the form of the gaseous state. It gives CH4, that is gas, plus H2O, that is in the form of the gases as well. And vice versa, the reverse reaction CH4 plus H2O gives CO and 3H2 here. We are here 4 mole of the gases reactant, that is the carbon monoxide and plus 3H2 here, becomes the 2 mole of the gaseous product, that is CH4 plus H2O here. And with regard of that, suppose equilibrium mixture for the above reaction kept in the cylinder fitted with the piston at a constant temperature is compressed to 1/2 of the original volume, and then the total pressure will doubled according to the PV, where we know that PV equals to constant. With regard of that, the partial pressure of the that partial pressure and therefore the concentration of the reactant and the product have changed, and the mixture is no longer at equilibrium. The direction in which the reaction goes to re-establish equilibrium can be predicted by applying the Le-Chartier's principle, and since the pressure has doubled, the equilibrium now shifts in the forward directions, in a direction in which the number of the moles of a gas or a pressure decreases. We know that the pressure is proportional to the moles of a gas as well. This can also be understood by using the reaction question, that is QC. Let that carbon monoxide and as well as H2, CH4 and H2O be the molar concentration of the equilibrium for the methanation reactions. And when we go ahead, so when volume of the reaction mixture is half, the partial pressure and the concentrations are double. So we obtain the reaction quotient by the replacing each equilibrium concentration by double its value. So here we have the QC is equals to CH4, that is in the form of the gases, plus that is an H2O gas, and CO carbon monoxide in the form of gas, and H2, and that is in the form of the gases here, as well as that is whole thrice. Where we talk about the QC is less than Kc, and that is the reaction proceed in the forward direction. In the reaction that is we have is C, that is in the form of solid plus carbon dioxide form in the form of the gases, that gives us carbon monoxide 2 of CO, and 2 CO, that is gives C, and that is the carbon monoxide carbon dioxide here. When the pressure is increased, the reaction gives in the reverse direction, and because the number of moles of the gases increase in the forward direction here. With regard of that, if I'm talking about, now we'll discuss some of the other point, that is effects of the inert gas addiction, and that is addition that we have to discuss here, and that is here. So here, effect of inert gas addiction here, if I'm talking about that, if the volume is kept constant and an inert gas such as argon is added, which does not take part in the reaction, the equilibrium remains undisturbed. With regard of this, we can say undistributed. It is because the addition, with regard of that, that is undistributed, it is because that the addition of an inert gas at a constant volume does not change the partial pressure or the molar concentration. The substance involved in the reaction and the reaction quotient changes only if added to a gas is a reactant or a product involved in the reaction here. With regard of that, we'll discuss about the effects of the temperature change here. And the effects of the temperature change, we talk about that whenever an equilibrium is distributed by a change in the concentration, the pressure and the volume and the composition of the equilibrium mixture changes because of the reaction quotient, that is Q, and that is no longer that is not longer equals to the equilibrium constant, that is Kc. And then however, when change in the temperature occurs, the volume of the equilibrium, that is Kc, is changed. In general, the temperature dependence of the equilibrium constant depends on the sign of, that is delta H for the reaction. And here these were the 2 points, that is that the equilibrium constant for an exothermic reaction negative, that is delta H, decreases as the temperature increases. जैसे temperature increase करता है, and then in an exothermic reaction the equilibrium constant that the negative is has been decreases here. With regard of that, the equilibrium constant for an endothermic reaction, the positive, and the increases as the temperature increases. जैसे temperature increase करता है, वैसे ये भी increase करता है. With regard of that, the temperature changes effect of the equilibrium constant at the rate of the reaction, and the production of that ammonia according to the reaction. We will go ahead with NO, that is N2 in the form of the gases plus 3H2 in the form of the gases, that gives 2NH3, and it forms it. And the delta H for this is minus 92.38 kilojoule mole inverse here. In regard of that, with this reaction, this is an exothermic process, and according to Le-Chartier's principle, that is resign the temperature shift at the equilibrium to the left and the decrease the equilibrium concentration of ammonia. And in other words, low temperature is favorable for a high yield of ammonia, and but the practically very low temperature slow down to the reaction, and thus catalyst is used. Now we'll discuss about the effect of the temperature and experiment. With regard of that, here you have to know some of the things related to this, that is what the effect of the temperature on the equilibrium that can be demonstrated by taking the NO2, what we are taking here, gases that is in brown in color, which demersed into the N2O4, that what you can see here, and that is the colorless as well. So I will just write it down here. The color that it forms is your brown, and this is your colorless. So for that, and 2NO2 gas is formed, that gives the N2O4 in the form of the gases here, and where the delta H you will be finding out minus 57.2 kilojoule mole inverse here. So here the NO2 gases prepared for the additions of copper turning to the concentration HNO3, that is collected in two that is 5 ml test tubes, that is ensuring the same intensity of the color of the gases in each tubes, and has a stopper sealed with the araldite, that is a 3 2 or 50 ml beakers, that is 1 2 3 containing the freezing mixture, and water at a room temperature and a hot water 363 Kelvin respectively are taken, and both the test tubes are placed in the beaker, that will make a beaker, and that the effect of the temperature on the directions of the reaction is depicted very well in the experiment. And at low temperature in the beaker, the forward reactions in the formations of N2O4 is prepared, and as the reaction is exothermic, thus the intensity of the brown color due to the NO3 decreases, and while a beaker 3 that have a high temperature favors the reverse reaction here, and which that formations of NO2, and thus the brown color that intensity intensifies. And even though effect of the temperature can also be seen in the endothermic reaction, and that is your COH2O whole 6 by 3 plus aqueous, and that plus 4Cl minus aqueous, and that gives COCl 4, and that is in aqueous state, and that is 6H2 in the form of the liquid state. This is in the color that it forms a pink color, and that is the colorless here, and it forms a blue color here. In regard of that, at a room temperature, the equilibrium mixture is blue due to the COCl4 2 minus, and when cooled in freezing mixture, the color is mixture turns pink due to the COH2O6 here. So now we'll discuss about the effect of catalyst, or what we have to discuss, as you can see, and about the effect of the catalyst here. The reaction we have is, but before the reaction start, we will go ahead with some of the deep related to the effect of catalyst here. In the terms of the effect of catalyst, a catalyst increases that the rate of the reaction, chemical reaction, by making the available a new low energy pathway for the conversion of a reaction to product, and it increases the rate of the forward and the reverse reaction that passes through the same transition state, and does not affect the equilibrium. As well as the catalyst lowers the activation's energy to the forward and the reverse reaction by exactly the same amount, where we can say that the catalyst does not affect the equilibrium compositions of the reaction mixture, and does not appear in the balanced chemical equations, so are in the equilibrium constant express. Let us consider that the formation of the NH3 from dinitrogen and the dihydrogen, which is a highly exothermic reaction, and that proceed with a decrease in the total number of the moles formed as compared to the reactants. Even the equilibrium constant decrease with the increase in the temperature, and at low temperature rate decreases, and it takes a long time to reach at equilibrium, whereas the high temperature gives the satisfactory rates but poor yields as well. And the German chemist Fritz Haber that discovered the catalyst consisting of iron, a catalyst and reaction of two occurred the satisfactory rate of the temperature, whereas the equilibrium concentration of NH3 is reasonable or favorable, you can say, and that since the number of the moles formed and the reaction is less than that of those of reactants, so the yield of NH3 can be improved by increasing the temperature here. The German chemist, what I had named it here, and that the name of that German chemist is your Fritz Haber. This is a German chemist. Okay, in terms of this, that optimum conditions of the temperature and the pressure for the synthesis of NH3 using the catalyst around 500 degrees Celsius at and 200 atm. Similarly, in the manufacture of the sulfuric acid by contact process, this is 2SO4 gas plus O2 gas that gives 2SO3 in the form of the gases, that is Kc equals to 1.7 into 10 to the power 26 here. And with regard of that, though the value of the K is suggestive of reactions going to the completion, but practically the oxidations of SO2 to SO3 is very slow. So thus the platinum or the divanadium pentaoxide, that is the formula of those we have is your V2, that is V2O5, is used as catalyst to increase the rate of the reaction. If the reaction has an exceedingly small, that is K, a catalyst would be of a little help here. Now we'll discuss somewhat related to the ionic equilibrium in the solution. In the ionic equilibrium or in the solution, what we have to discuss, that under the effect of the change of the concentration on the direction of equilibrium, you have to incidentally come across with the following equilibrium, which involves ions like Fe3 plus aqueous plus SCN minus aqueous, that gives FeSCN, that is 2 plus aqueous here, and with a reverse to it, that is FeSCN gives Fe3 plus and SCN minus here. With regard of that, there are the numerous equilibrium that involves ions only, and in the following sections we will study that the equilibrium involving ions, and it will knows that the aqueous solution of the sugar does not conduct electricity, and however when the common salt sodium chloride is added to water, it conduct electricity. And although also that the conduction of electricity increases with an increase in concentration of common salt, and that Michael Faraday classified the substance into the two categories, that is based on their abilities to conduct electricity. One category of the substance conduct electricity in the aqueous solution, and that are called as electrolyte, and the second, what he had classified as electrolytes, and the strong electrolytes on the dissociations in water are ionized and almost completely, and which while the weak electrolyte are only the partially dissociated. For example, in aqueous solutions of sodium chloride is comprised entirely of the sodium ions and chloride ions, while that of the acetic acid mainly contains the ionized acetic acid and that molecules, and only some acetate ions are and proton, and this is because there is almost 100% of ionization in the case of the sodium. And with regard of that basically that sodium chloride as compared to the rest of that 5% ionization of acetic acid, and which is a weak electrolyte. And it should be noted that weak electrolyte, that is equilibrium, is that is established between the ions of the unionized molecules, and this is a type of equilibrium that involving the ions in the aqueous solution is called ionic equilibrium. And with regard of that, so here with regard of that, the acid bases and the salts come under the category of the electrolyte and may act as either strong or as a weak electrolyte. Now we'll discuss about some of the things, that is acid bases and salts here. With regard of that, here for this, before starting with this, we have to know some of the things related to the acids, bases as well as the salt here. With regard of that, the acid bases and the salts like find widespread occurrence on the nature, and hydrochloric acid present in the gastric juice is secreted by the linking of our stomach and in a significant amount of like 1.2 silica 1.5 liter per day, and it is essential for the digestive process as well. And the acetic acid is known as to be the main constituent of the vinegar, lemon or oranges juices that contain the citric and the ascorbic acid, and the tartaric acid as well, that is found in the tamarind paste. And as most of the acid taste so, the word acid has been derived from the Latin word that is acidus, and meaning the sour as well. And acids are known to turn a blue litmus paper into the red and the liberate dihydrogen on reacting with the metals. And similarly, the bases are known to turn a red litmus paper blue, and that taste bitter and feel soapy. A common example for that base is washing soda using for washing purpose. And when acids and the bases are mixed in the right proportion, then they react with each other and to give salt as well. And where some commonly known examples of the salts are sodium chloride that we are using, that a common salt here, and that is the barium sulfate, sodium nitrate. Sodium chloride is a common salt that is an important component of our diet, and is formed by the reaction between the hydrochloric acid and the sodium hydroxide. And even though it exists in the solid state as a cluster of the positively charged ions, the sodium, and the negatively charged chloride ions, which are held together due to the charge species. And as well as that, the electrostatic forces between the two charges are inversely proportional to the dielectric constant of the medium. And water is a universal solvent, as I told, and that possesses a very high dielectric constant of 80. And where thus when the sodium chloride is dissolved in water, and that electrostatic interactions are reduced by the factors of 80, and this facilitates the ions of move freely in the solution, and also they are well separated due to the hydration with the water molecule as well. With regard of that the comparing the ionization of the hydrochloric acid with that of the acetic acid in water, we find that though both of them are polar covalent molecules, former is completely ionized into its constituent ions, and while the latter is only partially ionized, that is less than 5%. The extent of which ionizations occurs depends upon the strength of the bond and the extent of the solvation of ions produced. And the term dissociation and the ionization have earlier been used with a different meaning, and the dissociation refers to the process of the separations of ions in water, and that is already existing as such as like solid state of the solute. As in sodium chloride, on the other hand, the ionization corresponds to the process in which a neutral molecule is splits into the charged ion in the solution, and where we shall not distinguish between the two and use of the two terms interchangeable. With regard of that, we can say that dissociation refers to the process separations of an ions in water already existing in such the solid state of the solid, that in the sodium chloride here. And with regard on the other hand, the ionization correspond to a process which is a neutral molecule splits into the charged ions in the solution, and here we shall not distinguish between the two terms interchangeable. And that is, if I'm talking about the Michael Faraday, that you know very well about the Faraday, that Faraday was born near the London into the family of very limited means, and at the age of the 14 he has been appreciated apprenticed to a kind bookbinder who allowed a Faraday to read the books that was binding. And though a fortunate chance, he became a laboratory assistant to Davy, and then during 1813 to 14, and that Faraday accomplished him to be a continuant. And then during the trip he gained much from the experience of coming into the contact with many of the leading scientists of the time. And in 1825 he succeeded Davies as director of the Royal Institution laboratories, and in 1833 he also became the first Florian professors of chemistry. That Faraday's first important work was an analytical chemistry, and after 1821 that much of his work was an electricity and the magnesium and magnetism and the different electromagnetic phenomena. And his idea has led to the establishment of the modern field theory. and as well as he distributed his two laws of electrolysis in 1934. The Faraday was a very modest and kind-hearted person. He declined all honors and avoided scientific controversies. He preferred to work alone and never had any assistance. He disseminated science in a variety of ways, including the Friday evening discourses, and which he founded at the Royal Institute, and he has been very famous for his Christmas lecture on the chemical history of the candle, and he published nearby 450 scientific paper as well. In regard of that, we will discuss more other topic, that is your that is Arrhenius concepts of acids and bases here. With regard of Arrhenius concept here, in the case of the Arrhenius concepts of acids and bases here, with regard of that, according to the Arrhenius theory, that acids are the substance that dissociates in water to give the hydrogen ion and H plus aqueous, and the bases are the substance that produce the hydroxyl ions, that is OH minus aqueous. And the ionization of an acid, that is HX, that is in the aqueous state, can be represented by the following, that is HS, that HX, that is in the form of aqueous plus, that gives H plus aqueous and X minus aqueous here. With regard of that, we can say that HX in the aqueous form plus H2O, that is in the form of liquid, that gives H2O plus aqueous plus X minus, that is your aqueous here. A bare portion of H plus is a very reactive and cannot exist freely in the aqueous solution, and thus it bonds to be the oxygen atom of the solvent water molecules to give the trigonal paramedical hydronium ion, that is H3O. We had telling about like H3O, and this is the hydronium ion as well. And where these in this chapter we shall discuss about the H plus aqueous and the H3 plus O plus aqueous, interchangeable to mean the same at a hydrated proton. And similarly, a base molecule like MOH ionizes the aqueous solution. According to the equation, we form MOH aqueous, that gives M plus and OH minus and aqueous here. In regard of that, the hydroxyl ions also exist in the hydrated form in the aqueous solution, and that Arrhenius concepts of acids and base, however, suffers from the limitations of being applicable only in the aqueous solution, and also does not account for the basicity of the substance like ammonia, which do not possess a hydroxyl group as well. In regard of that, we will discuss about the Bronsted Lowrys acids and bases. Before that, we have to know about the hydronium and hydroxyl ion. That hydrogen ion by itself is a bare proton with a very small size, like near about 10 to the power minus 15 m radius, and intense electric field binds itself with the water molecule at one of the two available lone pair on its, giving H3O plus. And this species has been detected in many compounds, that is H3O plus Cl minus in a solid state, and in an aqueous solution the hydronium ion is further hydrated to give the species of H5O2 plus and H7O3 plus, and then H9O4 plus, that I can write it down if you want to know about it. And that is H5O2 plus, H7O3 plus, and then H9O4 plus. Here, similarly, the hydroxyl ion is hydrated to give the several ionic species like H3O2 minus, H5O3 minus, and H7O4 minus here. With regard of that, the structures have been maintained. Now we'll discuss about the Bronsted Lowrys acids and bases here, and that's what we have to discuss about this Bronsted Lowrys acids and bases here. The Danish chemist, the name of the chemist is Johannes Bronsted, and the English chemist also, I did write here, English chemist, the name of the English chemist is Thomas M. Lowry, gave a more general definitions about the acids and bases. And according to the Bronsted, first of all we have to know about the Bronsted Lowry acids and bases, then we'll discuss about the equation here. According to the Bronsted Lowry theory, that acid is a substance that is capable of denoting a hydrogen ion, that is H plus, and bases are the substance capable of accepting a hydrogen ions like H plus. In a short, acids are the proton donors and bases are proton acceptors as well. In the consider the examples that dissociation of NH3 here and the H2O, and we are representing the following equation like NH3 aqueous that is in the base state and that is H2O liquid that is in the acid state. It gives NH4 plus and OH minus. These both are in aqueous state, and this is the conjugate acid and this is the conjugate base. From base to the conjugate acid that is adds proton, and from acid to conjugate base that is the losses proton here. Okay, the basic solutions is formed due to the presence of the hydroxyl ion, and in this reaction the water molecule acts as proton donor and ammonium molecule acts as a proton acceptor and are thus called the Lowry Bronsted acid and the bases respectively. It is in the reverse of the reaction here that H plus and that is transferred from the NH4 plus and to OH minus, and in this case the NH4 plus acts to the Bronsted acid while the OH minus acted as the Bronsted base, and the acid the bases the pair of the differs only by one proton, that is called conjugate acid base pair, and therefore the OH minus is also called the conjugate base of an acid that is H2O, and NH4 is called the conjugate acid to the base that is NH3. And if the Bronsted acid is strong acid, then its conjugate base is a weak base and the vice versa. It may be noted that the conjugate acids has one extra proton and each conjugate base has one less proton here. We will consider the example of the ionization of the hydrochloric acid of water as here, and that is HCl aqueous acts as an acid and donating a proton and to H2 molecule which act as a base. So here we have an HCl, as you can see, that is in the form of the aqueous state and that is in solid as acid, and that plus H2O that is in the base form of liquid. It gives H3O plus that is conjugate acid and Cl minus aqueous that is your conjugate base. From the base to the conjugate acid that adds proton, and from acid to conjugate base that lost proton here. Now with regard of that, it can be seen in the above equations that water acts as a base because it accepts the proton, and there's a species of H3O plus is produced by water as a product here, and that base of an acid H3O and H3O plus as well, and is a conjugate acid of a base of H2O. It is interesting to observe that the dual role of the water as an acid and a base. In case of the reaction with HCl, water acts as a base, while in the case of ammonia, it acts as an acid by donating a proton here. Talking about the Svante Arrhenius, you want to know about it. So that is Arrhenius was born near the Uppsala, Sweden, and he presented his test and on the conductions of electrolyte solution to the University of the Uppsala in 1884. For the next 5 years of the traveled extensively and visited the numbers of research centers in the Europe. In 1895 he was appointed professor of physics at the newly formed University of the Stockholm, and serving as a rector from 1897 to 1902. From 1905 until his death, he was a director of the physical chemist at the Nobel Institute of the Stockholm, and he continued to work for many years of electrolyte solutions. And in 1899, he discussed the temperature dependence of the reaction rates on the solutions. And in 1899, he discussed the temperature dependence of the reactions rate on the basis of an equation, and yes, and now usually known as the Arrhenius equation here. And even though he worked in a variety of the fields, like made important the contribution to the that is your immunochemistry, cosmology, and the origins of the life and the causes of his ice age, and he was the first to discuss the greenhouse effect, calling by that name. He received Nobel prizes in the chemist in 1903 for his theory of the electrolyte dissociation and its use in the development of the chemistry as well. Now we'll discuss the question here, and that is your what will be the conjugate base for the following Bronsted acid that we have here is your HF and H2SO4 and as well as HCO3. In reference to that, the conjugate base should be one proton less than each case, so therefore the corresponding conjugate would be your F minus, HSO4 minus, and CO3 2 minus. So this will be your conjugate base for that following Bronsted acids here. Okay, now we'll go ahead with another one here. That is, the question is, write the conjugate acid for the following Bronsted base, that is NH2 minus, NH3 and HCOO. Okay, with regard of that, the conjugate acids should have one extra proton in each of the cases, and therefore the corresponding conjugate acids will be, for NH3 it will be NH3, NH2 minus वाले के लिए NH3, and then we have your NH NH4 plus and HCOOH. These are the respectively. For the next question we have this, that the species H2O, HCO3 and HSO4 and NH3 can act both as your Bronsted acid bases, and for each cases give the corresponding conjugate acid and the conjugate base here. In regard of this, if I'm talking about, so here, and the answer is has been given in the solution would be in the form of the table, so we'll just find it out the table here. First we will be writing out here the species, then the conjugate acid and the conjugate base. Okay, so it would be like this. स्पेशीज की बात करती हूँ तो पहला है H2O, सेकेंड is HCO3 minus, HSO4 minus, and then we have NH3. For these, the conjugate acid for the first one we have here is your H3O plus, and for that conjugate base is OH minus. This for this is H2CO3, this is CO3 2 minus, H2SO4, this is SO4 2 minus, and for last is NH4 minus, and here this will be NH2 minus. For today's class, this is what we have to end up with. And first of all, it's a huge request कि अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो, सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुंचे। एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगा हो तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो, सो दैट ज़्यादा से ज़्यादा लोग के पास वीडियो पहुँचे और ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सकें। इन द टर्म्स ऑफ द यूटिलाइजेशन, एज आई एम टेलिंग यू कि हम लोग ने बहुत सारे यूनिट्स अभी ऑलरेडी कवर अप कर लिए हैं। ये हम लास्ट यूनिट केमिस्ट्री की चल रहे हैं, जो कि हमें ऑलरेडी आपकी, अगर हम केमिस्ट्री की बात करते हैं एनसीईआरटी की, तो हम उसमें हमने यूनिट 1 कंप्लीट किया है, जिसमें सम बेसिक्स कॉन्सेप्ट्स ऑफ केमिस्ट्री है। उसमें अगर हम बात करते हैं तो वी हैड कवर अप द इंपॉर्टेंस ऑफ केमिस्ट्री, नेचर ऑफ मैटर, प्रॉपर्टीज ऑफ मैटर एंड देयर मेजरमेंट्स, अनसर्टेनिटी इन द मेजरमेंट्स, एज वेल एज लॉ ऑफ द केमिकल कॉम्बिनेशंस एंड Dalton's atomic theory, atomic and molecular masses, more concepts of and molar masses, percentage composition and stoichiometry, and the stoichiometric calculation as well. In the second unit, we had covered up the structures of atom, where the subatomic particles, atomic models, development leading to the Bohr's models of atom, and Bohr's model for the hydrogen atom, as well as the toward quantum mechanical models of an atom, and even the quantum mechanical model of atom, that what we had discussed here. In the classifications of the elements and the periodicity in the properties that we had discussed, why do we need to classify elements, genesis of periodic classification, modern periodic laws and the present laws of the periodic table, nomenclature of the elements with the atoms that is greater than 100, electronic configuration of elements and the periodic table, electronic configuration and the types of elements, as well as for the S block, B block and D block and F block, periodic trends in the properties of elements here. And then after that, what we had cover up, and the next, that is your unit 4, that is the chemical bonding and the molecular structure, where we had cover up about Cartels-Lewis approach to the chemical bonding, ionic electrovalent or electrovalent bond parameters, the valence shells, electron pure repulsion theory, and then valence bond theory, hybridization, molecular orbital theory, bonding in the some homonuclear diatomic molecules, and hydrogen bonding. States of matter में intermolecular forces, thermal energy, intermolecular forces versus thermal interactions, gaseous state, gaseous law, the ideal gases law, kinetic theory, molecular theory of the gases, behavior of real gases, deviations from the ideal gas behavior, and the liquefaction of the gases, liquid state. That's what we had covered up. In the unit 6, we had started thermodynamics, thermodynamic state, application, measurements of delta U, delta H, calorimetry, enthalpy change, delta R of H of reaction, Then enthalpy for the different types of reaction, spontaneity, Gibbs, energy change और equilibrium. Then unit 7 में equilibrium जो हमने start कर दिया, equilibrium in the physical process we had completed, equilibrium in the chemical process, dynamic equilibrium we had completed, law of chemical equilibrium and the equilibrium constant we had completed, homogeneous equilibrium we had completed, heterogeneous equilibrium we had completed, applications of equilibrium constant we had completed, relationship between the equilibrium that we had completed here, and then after that relationship between equilibrium constant K and reaction Q and the Gibbs energy that we had completed today. Factors affecting equilibria we had completed today. Ionic equilibria in solution we had completed today. Acid, base and salt we had completed today. And ionizations of acids and bases, that what we have to discuss in the next coming classes, and the buffer solution, then solubility equilibria of the Spangli soluble salt, that what we have to complete in the next coming classes. And hopefully in the next coming classes we will end up with this chemistry as well. So first of all, it's a huge request, go through with the subscribe button and please like, share and subscribe our channel. Thank you, hope you enjoyed this video. If you like this video, please give a thumbs up and give your suggestion in the comment box. Thank you.